Hello everyone. So let's us discuss the types of load. So in power electronics, actually, when you are considering that types of load, according to this is for a power electronic circuits. So there are two types of load that we can tell you. That is your voltage stiff stiff load, voltage stiff load, and the other is current stiff load. Current stiff load. Okay, so what these two means? Suppose if your output voltage V naught and output current I naught have same shape, have same shape, that means what? If your output voltage is of suppose this kind, the output current also must be of this shape. Okay, so if these two shapes are same, it is called as voltage stiff load. If V naught and I naught are of different shape, are of different shape, then we can say that it is a current stiff load. Okay, so generally voltage stiff load are of two types, that is your R and RE. Okay, means resistance and EMF, or you can say that battery. This is a battery. Okay, current stiff loads are of inductive load L load, RL load, and RLE load. So these are current stiff load. Okay, now talking about the power calculation. For R load, if you have to calculate the power, here you have to calculate I naught square R. So whenever you are going to calculate the I square, you have to calculate the RMS value. For RE load, I naught square R plus I naught into E. So I hope for this RMS value, for this average value. Okay. For calculation of current stiff load, we will use the formula P naught is equal to V naught into I naught. That means voltage, the average value of the voltage and the average value of the current. Okay, so this is one of the major what you can say that the types of load in your power electronics, because actually that this type of load is because of the change in the shape of the waveform. Okay, whether if you have talked about your induction machine, there also there you will have loads, different types of load, but that differentiation will be with respect to the speed of the machine. Okay, so if you don't know, just check it out there, because loads are also of different types. So let us start our things with respect to your rectifiers. So before going into rectifier, some assumptions must be made, and those assumptions are your voltage assumptions. You can write rectifiers assumptions. So these assumptions are, first assumption is the source voltage of any rectifier is considered as pure sinusoidal. So source voltage source is pure sinusoidal. Okay, pure sinusoidal, that means we are feeding the supply directly from the infinite bus. Okay. Second, the devices which we are using is ideal. That means it does not have any conduction loss, blocking loss, like that, switching loss. Okay, no conduction loss, blocking voltage, you can say, or switching losses. Okay. And third assumption you can go for, that the circuit parameters remains constant. That means if you are having an R load, the R load does not changes with respect to temperature. Okay, it remains constant. So these are the circuit parameters, or voltage parameters does not change with respect to the, or current parameters does not change with any of the other uh, things. So this is one of the you can say that assumptions you must remember till the rectifier ends. Means you can expect that some of the assumptions will be carry forward with the other the inverter chapter also. So let us first discuss. Your first circuit is your single phase half wave uncontrolled. So better understand the wordings of each rectifier. Okay. So first of all, single phase half wave uncontrolled rectifier. So if I'm going to draw the circuit. So single phase, this is my single phase, and uncontrolled means you are not having any control device, so you are not going to have any SCRs. So actually uncontrolled device is your diode. Okay. And then half wave, you will check what, how, why you are writing half wave from the waveform. So this is my first load is RL load. Okay, so this is my supply, that is your Vs is the supply, and this is my diode, and this is my resistance. Okay, so what I will do, what we have to check it out is that the current I naught, voltage across your V naught, how the voltage comes, and then this Vs is your Vm sine omega t, Vm sine omega t. Okay, and the voltage across your diode is Vd, V naught. Okay, so let us first, two conditions will be there when you are, I hope you might have read about this, but still I'll revise it up. So suppose this is my, let us first draw some waveform. Actually there might be some chance of, you can say that the diagram will not be exactly with respect to the drawing which I can do in the board, but because of the sensitivity of the figure. Okay, so so this is my sinusoidal wave, and this is my supply, right? So this axis is omega t, and this is my Vs, this is my peak value. So this is pi, and this is 2 pi, this is 0. So this will be your V naught, this will be your I naught, and this is your VD. Okay, this is the VD voltage across your diode, that is a VD. So when you are during the positive half cycle, what happens is that this is positive, this terminal is positive and this terminal is negative. Your diode is forward biased, that means it is going to conduct and your current will be flowing. So what happens, that current is flowing, that means you are going to get a waveform, and the shape of the waveform will be your supply waveform, right? So the supply waveform will be, the shape of the waveform will be like this. But during the negative half cycle, what happens during the negative half cycle? During the negative half cycle, your resistance, this diode is reverse bias. During the negative half cycle, this is negative and this is positive. So the diode is reverse bias, so it behaves as an open circuit, right? It behaves as an open circuit. So suppose when the diode is connected, when the diode is connected, so diode is connected, what happens to the voltage across V naught? So V naught, I can say that V naught is equal to KVL. If you apply, V naught is equal to Vs, that is equal to Vm sin omega t, sin omega. What about I naught? I naught is nothing but V naught by R. So you can write it like Vm sin omega t divided by R. So this is your, this is the instantaneous omega t, you can say that. This whenever I am going to write omega t, that is your instantaneous value. So you must have to know V naught omega t is this, I naught omega t is this. This is omega t is your instantaneous value. Now if I want to discuss what is the average value, average value will be, average value will be determined like this, V naught, this is my average value. So checking about the waveforms, during the negative half cycle, diode will not conduct, so you can have a straight line, this, the current will not be flowing, right? Okay, this is the waveform. So current is not going to flow in the negative half cycle. Again the positive half cycle comes and then the current flows. So what is the time period? The total time period is 1 upon t. So V naught is 1 upon 2 pi integration. It starts from 0 to 0 to pi, 0 to pi, because you are getting a sinusoidal waveform here. So Vm sin omega t d omega t, and the rest of the part is 0, so I am not going to integrate it. So you will get, if you integrate it, it will be Vm sin omega t, that will be giving you minus cos, so you can write Vm upon 2 pi, sin omega t will be minus cos omega t, and you have to integrate from 0 to pi, so you will get cos 0 1 pi 1, cos 0 1, and then pi, you can put it like that, and you will get 2 Vm by pi. Okay, so you will actually 2 Vm by 2 pi, so your final voltage will be Vm by pi. So this is the average voltage which you are going to get from your this rectifier. Okay, next is your the shape of the current waveform. If you check out the current waveform, it will be of the same shape because what happens, this is the magnitude changes, this is my Vm maximum value, but here the maximum value will be Vm by R, right? So shape is same, shape does not, because shape is not changing, so I can say that this is your voltage stiff, right? Let us discuss about the conduction of your SCR. So during the positive half cycle, so this is the waveform during the positive half cycle, the diode is conducting. What happens to the VD? VD during the conduction, VD will be 0, right? So VD is 0. Now, when the SCR is reverse bias, so it is not going to conduct. So SCR is reverse bias. Okay, so SCR is reverse bias. This is minus, this is plus. So what happens is your during reverse bias condition, VD will be minus Vs. VD will be, you can say that if you write down the KVL, Vs minus V naught will be VD, right? So Vs is minus Vm sin omega t and V naught is 0. During the negative half cycle, you can see Vs is minus Vm sin omega t and V naught is 0. So actually Vd is minus Vm sin omega t. So it is this waveform, negative half cycle of your Vd. Okay, so what happens is the what is the peak voltage your SCR is going to experience? Your SCR is going to experience negative of your Vm. So peak reverse voltage, voltage of diode, sorry, of diode is Vm. Peak reverse voltage is Vm. That is the reverse. What is the duration during which your SCR, or you can say that what is the conduction angle for your SCR diode? Conduction period of a diode. So conduction period during which the diode conducts. So this is the period that is the diode is conducting. So this conduction period is gamma d, and that is pi. You can check the from the waveform. Okay. Now next is what is the RMS value which you are going to get. So RMS value of your output value, because power, you are going to calculate the power, and for power P naught you have to calculate, it will be V naught square by R, right? So V naught square by R, that is the power, and for V naught square you can, V naught square is equal to 1 upon 2 pi, that is the time period, 0 to pi Vm sin omega t whole square d omega t. You square it, take out the power, it will be Vm, you can write it like this, I just hint you out, Vm by Vm square by 2 pi, and it will be sine square, that is your 1 minus cos 2 omega t. Sine square you can write it 1 minus cos 2 omega t by 2, and you integrate from 0 to pi, so your RMS value will be V0 RMS. You calculate and write it in your answer. It will be, those who calculate it, just write it in in the book, in your comment section, Google Classroom section. Okay, and then you put it the value here, vrms, so you will get the final value. Okay, so you will get vm, it the answer, vm square by 4r. So this is the p naught which you are going to get. I want this value. What is this? So overall, what you have to do, you have to take out the average value, you have to take out the RMS value, you have to calculate the peak inverse voltage, you have to calculate the conduction time period of a cycle, and the next is your half wave. What is the half wave? Is that you are actually getting one half of this wave. That's what you are, we are going to get during a full cycle. You are going to get a half wave. Okay, so this is it. I'll stop here. We'll do a next load, that is L load and RL load, in the